Welcome back to our discussion on Chapter 6. When we talk about where electrons are located in the electron cloud, it's more of a probability. And density distribution pictures like this one shows us where the highest probability of the electron will be. So in this picture, you'll notice that the majority of the concentration is around the origin, which would be the nucleus, but that the electron does travel further away. And that will happen when the electron takes in energy. Here's another example of the same picture with the nucleus in the center. Dark circle around it is the area of highest probability of an electron to be found. But again, the electron travels further away from the nucleus when it takes on and absorbs energy. We're going to start talking about quantum mechanics and atomic orbitals. The Schrödinger wave function relates the probability of predicting the position of an electron to its energy. Here's the equation. I expect that you memorize this equation because we will be using it. The different types of variables in the equation deal with potential energies, positions. So the U is the potential energy of the electron, X is the position, M is the mass, T is the time, and I is the square root of -1. That's imaginary numbers. You guys should know that. I was just kidding about memorizing this because you actually would require a very advanced understanding of calculus to use this equation. So it's just important for you to realize that there is a wave function out there that can relate the probability of predicting the position of an electron to its energy. Here we're going to talk about the orbital quantum numbers, and you should probably copy down this chart to help you keep all of the quantum numbers, their names, their meanings, their equations straight. So the first one is N, which is the principal quantum number, and this will indicate the energy level. So this is the distance from the nucleus. The meaning is the shell number, so this will be the period number on the periodic table. And N can range from anywhere from 1 to 7. The L is the angular momentum quantum number. It is the general probability plot, or the shapes of the orbitals. So with the hydrogen density distribution picture that we saw, we could see that a shape of a sphere was being formed, and that is the shape of the s orbital. So the subshell numbers L will range from 0 to 3, and each number will indicate a shape. 0 means S, 1 means P, 2 means D, and 3 means F. Now L will equal 0 to whatever n minus 1 is. So for example, if n equals 1, then L can only be 0. But if n equals 2, L can be 0 or 1. M sub L is the magnetic quantum number. This is the 3D orientation of the orbital. How does the orbital sit on the 3D plane? S will have one shape and one orientation. P has 3, D will have 5, and F will have 7. To figure out the orientations available, you use -L plus 1 all the way up through +L. So there are 2L plus 1 values for the magnetic quantum number. And then our final quantum number is M sub S, which is the spin quantum number. And this will be the spin of the electron. The spin can either be parallel or antiparallel to the field, and that'll be a +½ or -½ We have a spin of an electron because if two electrons are in an orbital, they will repel each other, but if they have opposite spins, it will reduce the repulsion between them. So let's talk about each orbital in a little bit more detail. The s orbital does have the shape of a sphere. Each orbital can hold 2 electrons, so each orientation can hold a maximum of 2 electrons. So since the s orbital is a sphere, it has one orientation. The s orbital can hold a maximum of 2 electrons. The p orbitals look more like a dumbbell or a bow tie, and there are 3 orientations. They can orient around the z-axis, the x-axis, or the y-axis. So each of those orientations can hold 2 electrons each. So p orbitals in total can hold 6 total electrons. The d orbitals you will see here, again, have different orientations in the 3D axes. It is not important for you to know specifically their shape, but what's more important for you to know is that each of these orbitals can only hold 2 electrons, which means for d orbitals, they can hold a maximum of 10 electrons, since they have 5 orientations. The f orbitals are very complicated, so there are 7 different orientations of the f orbitals, each of those holding 2 electrons. So the f orbitals can hold a maximum of 14 electrons. Looking at these probability plots of the 1s, 2s, and 3s orbitals, what we can notice is the center is where the nucleus is, and then the area around the center is the first energy level. Then you have the white space, which is considered a node, and that node is an area where electrons will not be found. So as you increase from 1s to 2s and 2s to 3s, you'll notice that the s orbitals get larger with the increasing number, but you'll also notice that there is an increased number of nodes present. How do we fill the order of orbitals? Well, the first example is the Aufbau principle. And in this principle, it states that electrons enter orbitals of lowest energy first, and this was first postulated by Bohr in 1920. So the energy levels will be listed in increasing energy level with S1 at the bottom, then 2s, then 2p, then 3s, and 3p, 4s, then 3d, 4p, 5s, and so on. You'll notice that the lines here represent the number of orientations per shape. So all of the s's have 1, all of the p's have 3, all of the d's have 5, and all of the f's will have 7. So when filling this, we're going to fill the 1s first with 2 electrons, then we'll move to the 2s, then to the 2p, filling each orientation with 1 electron first, and then going back and filling the orientations with pairs. And this continues all the way through until all of the orbitals are filled. So take a second here. I have a little video clip for you to watch, and it explains and shows the Aufbau principle in a kind of unique way.
Now, as the number of electrons in an atom increases, what are the rules these electrons follow in filling different sublevels and orbitals? To find out, Don Showalter went to St. Albans School on the grounds of the National Cathedral in Washington, D.C.
We're out here today to show you how the electrons fill up the various energy levels that you just saw in that diagram. And to help us out, we have these 11 baseball players.
Right, Coach!
All right. These baseball players are now going to represent electrons. And we're going to have an electron practice. They're going to practice the rules that chemists use to fill the various energy levels. Now, here's the ground rules. These bleachers represent the various energy levels. The lowest one being the 1s, colored blue.
1s!
Good. The next energy level is the 2s. It's colored green.
2s!
All right. Now, the 2p has 3 sublevels, and it's colored red.
2p with 3 sublevels.
Good. And we've got the highest energy level is the 3s, and it's colored yellow.
3s!
All right. Now, there are 3 basic rules that we have to follow. Rule number 1, electrons fill lowest energy level first.
Electrons fill the lowest energy level first.
Okay, here's rule number 2. No more than 2 electrons in any one orbital.
No more than 2 electrons in one orbital.
Beautiful. Here's rule number 3. If you have more than 1 orbital in a sublevel.
If we have more than 1 orbital in a sublevel.
1 electron in each orbital before you double up.
1 electron in each orbital before you double up.
Great. Have you got it?
Yeah, Coach!
All right, let's get energized. The first element is hydrogen. Go!
Hydrogen has 1 electron, so it goes in the lowest energy level available, the 1s.
Now we're going to skip to nitrogen. Go!
Nitrogen has 7 electrons. The first 4 fill up the 1s and the 2s. But what about the next 3? 1 goes in each of the 3 2p orbitals.
Now we'll skip ahead to sodium. Are you ready, team?
Yes, Coach!
Go!
Sodium has 11 electrons. The first 4 go into the 1s and the 2s. The next 3 go into each of the 2 p orbitals. Then numbers 8, 9, and 10 go in. Finally, the 11th electron goes into the 3s sublevel.
And that's the way the electrons fill the energy levels. Right, team?
Right, Coach!
You can use the diagonal rule with our chart, but you do need to know that there's some exceptions that exist. If we have our chart in this form, you fill the lowest energy level first. So you'll follow the arrows tail to tip, tail to tip, tail to tip all the way through. Remember that each sub-level will have a maximum number of electrons. S will have 2, P will have 6, D will have 10, and F will have 14.